Welcome children. Today we are going to see the fundamental theorem of arithmetic, that is the basis for arithmetic. Before going into the theorem, first let us take a number, say 72. See, you are going to decompose this number 72, that is we are going to factorize. So, can you factorize this number? What do you mean by factorization? Writing as a product of different numbers. Now, you are going to write 72 as a product of some numbers. So, you can do this in many ways. One may say that 72 can be split as 8 into 9, and the other student will say that 72 can be split as 4 into 18, and the other way is writing as 3 into 24, and one more way 2 into 36, and one more way is there as 6 into 12. So, these many ways are there writing a number as a product of some numbers. But if you decompose further, that is if we decompose 8 and 9 further, we can split it and finally arrive as 2 into 2 into 2 into 3 into 3. Likewise, the same can be done for all the decompositions. That is, we are arriving at the final stage of decomposing into prime numbers, that is we cannot further decompose it. So, we are going to decompose all the numbers, we are going to split all the numbers as the product of primes. So, as we have written so many ways, but it says that there is a unique way. Can you arrive at a unique way? Observe all these are written in a different way. But if you observe, there are only 3 2's in every product. We can say that there are 3 2's and 2 3's. So, we can write 72 as 3 power 2 into 2 power 3 or 2 power 3 into 3 power 2. So, this is a unique way. In any way you can follow and write 72 as only this. So, this is the final answer we get after decomposition into prime numbers. So, any number, any composite number can be uniquely represented as the product of powers of primes. This is our theorem. This is otherwise called as unique factorization theorem. That is, I repeat the theorem as every composite number can be written as the product of powers of prime numbers. The order may vary, except for the order may vary, but we will get the unique factorization. So, this can be generalized as any natural number except 1 is either prime or can be represented as product of powers of prime numbers in a unique way. So, this is called as fundamental theorem of arithmetic. This theorem is very much useful not only in mathematics, but also in some other fields. See, this theorem says that prime numbers are the building blocks of any number. We can write any number except 1 as the product of primes or the primes itself. So, any composite number can be written as the product of prime numbers in a unique way. That is the major thing. And one more thing, we can say if any prime number p divides the product of two numbers, that is a and b can be taken as two numbers, and if you take the product ab and if p divides this product ab, we will say that p divides either a or b or both a and b. But this is not so for a composite number. If you take a composite number which divides the product of a and b, then we will say that composite number may divide a or it may divide b or it may divide the product, but it is not so for the prime number. I repeat, that the prime number, if prime number p divides the product of two numbers, it either divides a or b or both a and b. So, this is one of the most important applications of this theorem. And one more application we are going to use now is to derive HCF and LCM. Okay, we are going to apply this theorem to derive the HCF and LCM of numbers. One more application of this theorem is to say whether 1 is a prime number or not. Can you say, is 1 a prime number? No, 1 is not a prime number. Why? Yes, using this theorem we are going to prove that 1 is not a prime number. So, we can take a number, let us take 6. If you decompose this 6, that is if you factorize using prime numbers, we can factorize like this. But if 1 is a prime number, we may write 1 once or twice or thrice, or yes, the power may vary. So, you can't say that this is 2 power 1 and 3 power 1 into 1 power how much? So, we can't say this particular number. As the theorem says that the product is unique, you cannot include 1 here. So, which says that 1 is not a prime number. So, this is one of the results of fundamental theorem of arithmetic. Since this theorem says that the decomposition of any composite number is unique except for the order, we can use this theorem to solve some problems given. Now, look at the problem. Here a factor tree is given. We are going to find the values of m and n in this factor tree. As we are going to apply this theorem, we are going to go from the bottom, that is 5 and 2. This factor tree means that this placeholder, this box is split into 5 and 2. So, which number can be placed? Very good. 5 into 2 is 10. So, the number to be placed in the placeholder is 10. Can you understand? This order may vary. So, this is a product of these two numbers, so which is 10, and here we are going further. So, n is a product of these two numbers. So, n can be written as 5 into 10. What is 5 into 10? Yes, 50. So, n here is 50, and if you go further, the product of 3 and n is this placeholder. So, the product of 3 and 50 is 150 is the blank to be filled. So, 150 is the answer, and see the topmost 2 into 150 is our m. So, m is yes 300. So, we have applied the theorem and found the answer. See the next question, can 6 power n end with 5? Give reason. Can 6 power n, so n is a natural number here, n belongs to natural number. So, see 6 is an even number, even though it has more powers. Any number which is even in the product, it gives even number, that is a number into an even number is always an even number. So, 6 power n is always even. Can any even number end with 5? No. So, the answer is no, because what is the reason? 6 power n is always even, So, an even number can never end with 5. This is our answer. Okay. See the sum is 7 into 5 into 3 into 2 plus 3 is a composite number. Is it a composite number? Before going to the sum, we can discuss what a composite number is. We know very well a composite number is a product of prime numbers, that may be 2 or more prime numbers. A number, if it is written as a product of 2 or more prime numbers, then it is a composite number. So, let us see whether we can write this number as a product of prime numbers. Let us take the number and look at this number, this product. Here we have 3 and here in this term also we have 3. Shall we take out 3 common? Yes. So, 3 can be taken out and we can write this number as 7 into 5 into 2 as we have taken out 3, plus here 3 can be represented as 3 into 1. So, that is 1. As we have taken out 3, 1 remains here. So, we can say that we have written this number as a product of 3 and another number. Let it be a composite or a prime number, but we have written this number as a product of 2 numbers, which says that this number is a composite number. Okay? Let us move on to the next sum. See, a and b are 2 positive integers such that a power b into b power a is equal to 800. Find a and b. We know that any number will be written uniquely as a product of powers of prime numbers. So, we are going to write 800 as a product. So, we are going to split 800 as using prime factorization method. So, I am going to split 800 as 2 into 400, again 2 into 200, again yes, and so on as. So, how can we write this factorization? Yes, as 2 power 5, as 5 2's are there, we can write this as 2 power 5 into 5 power 2. So, as we have written 800 as 2 power 5 into 5 power 2, we are going to observe these. So, here a power b, instead of a power b we have 2 power 5 and instead of b power a we have 5 power 2. So, we can replace a as 2 and b as 5 or vice versa. So, a and b are 5 and 2. Can you understand? See, for what values of n, 4 power n can end with 6. Let us see the powers of 4, that is the value of 4 power 1 is 4. So, as n is natural, let us take from 1. So, 4 power 2 is 16 and 4 power 3 is 64, 4 power 4 is 256. See, 4 power 1, that is if the power is odd, it ends with 4. Look at these 3. If you go further, yes, it will end with 4. If the power is even, the value ends with, yes, very good, 6. So, we can say that if n is even, then 4 power n will end with 6. So, this is our answer. So, n should be even to get the value, the number to end with 6. Okay. Let us move on to the next sum. Look at the sum. If m and n are natural numbers, for what values of m does 2 power n into 5 power m end with 5? So, like the same sum we have seen already. Can you guess the answer? Yes. See, 2 power n into 5 power m, as n and m are natural numbers, definitely 2 will be there in the product. That is, this number has 2 in its decomposition, which means the number is even. Very good. Will an even number end with 5? No. So, this will never happen. That is, for no value of m, this number will end with 5 is our answer. Okay. So, we never get 5 in the unit place of this number is our answer. Look at the sum. Here 13,824 is equal to 2 power a into 3 power b. What is the value of a and what is b? So, here we have to factorize this number using prime factorization. We are going from the least number to the larger number. See, from 2 we are going to factorize, and up to we have decomposed the number fully with the prime numbers, we are going to stop. So, we have to write all these as the product, that is, this number should be written as 2 into 2 into 2 into 9 times as this, and 3 into 3 into 3 3 times. So, we have written like 2 power 9 into 3 power 3. If you compare this with the given question, here a can be replaced with 9 and b can be replaced with 3. So, a is equal to 9 and b is equal to 3 is our answer. Look at the sum. This number should be split as p1 power x1 into p2 power x2 into p3 power x3 into p4 power x4, and p1, p2, p3, p4 are the prime numbers written in ascending orders. Okay. Shall we decompose? Using prime factorization, we can decompose as like this. Okay. So, after decomposition, we will write as 2 power, how many 2's are there? Count, how many 2's? 3 2's. So, 2 power 3. How many 3's are there? Here 1, 2, 3, 4 3's are there. So, 3 power 4 into 5 is occurring 2 times. So, 5 power 2, and 7 is present only once. So, 7 power 1. So, if you compare these two, we can say that P1 is 2 and P2 is 3, P3 is 5 and P4 is 7. And what are our x1, x2, x3 and x4? All the powers of the same numbers, that is x1 is 3, x2 is 4, x3 is 2 and x4 is 1. So, we have completed this sum. One more application of this fundamental theorem is finding HCF and LCM. See, look at this example, that is, we have taken two numbers 40 and 50. 40 can be decomposed as 2 into 2 into 2 into 5, that is 2 power 3 into 5 power 1, and 50 can be written as 2 power 1 into 5 power 2. Seeing the HCF of 40 and 50, we have to take the numbers which are present in both 40 and 50, and we have to take the least power of that number, that is 2 is present in both the numbers, we have to take 2 and take the least power of that number, that is 2 power 1 here, here 2 power 3, which is the least number in the powers 1. So, the least among those two powers should be written for HCF, and we have to multiply further with the common number which is present in both the numbers in the decomposition. So, 5 is present in both the numbers, we have to take 5, and here also we are going to look at the least number possible. So, here 1 and here 2. So, we have to take the least number which is 1. Okay. So, HCF is nothing but product of the numbers which have least powers. We have to take the least powers of the numbers which are in the product of the numbers which we want to take the HCF, and we have to take what is LCM. LCM is nothing but we are going to take the product of all the numbers whose powers are the highest. See, the common number here present is 2. The highest power of 2 is 3. So, 2 power 3 should be multiplied, and 5 has the highest power as 2. So, 5 power 2 should be multiplied. So, this is our LCM. If there happens a number which is not common, let us take some x is present, some number is present in one number which is not present in the other number, then we have to take that x as, let us take this x. If this x is having a power 2 and here x is having a power 0. Suppose we have one more number here, that is here we do not have x, that is represented as x power 0. Can you understand? This number is present only in this number, but not here. So, we are going to take this as x power 0. So, applying the same theorem, we will be having in HCF, we will be having the least power as x power 0, and in LCM, we will be having x power 2. Can you understand? See, we are going to find the HCF and LCM of the given numbers using our theorem. 2,52,525 and here 3,63,636 are the numbers given. We are going to split the numbers using factorization. So, we apply prime factorization and get the numbers as, yes, 25, 25, 25 can be split as 5 power 2 into 3 power 1 into 7 power 1 into 37 power 1. And further, if you split that number, that is 36, 36, 36, we will be getting 2 power 2, 3 power 3, 7 power 1, 37 power 1 into 13 power 1. So, let us apply the theorem which says that the least power should be taken for HCF. So, we are going to take the numbers which are present common in both the numbers. See, 2 is not here. So, we can say that 2 power 0 is here and we are going to multiply 2 power 0 which is 1. So, we leave that 2 power 0. Then take 3. So, 3 power 1 is the least among these two. This is, yes, little. So, 3 power 1 and 7 is common and the least power of 7 here is 1 and 5 is not common. Here it means that 5 power 0 is there. So, 5 power 0 is the least one which is 1, we are not going to have this, and 37, yes, 37 power 1. So, these should be written as the HCF, multiply and say the answer, and we are going to find the LCM. LCM is 3 power, the highest number is 3 and 7 power 1, 37 power 1 and one more 5 power 2 should be written as the largest power of 5 is 2 and 2 power 2 which is present here should be written again, 13 also should be multiplied. So, this is our LCM. So, multiply and find the answer of HCF and LCM. Now, we are going to find the number which is the largest 6 digit number which is divisible by 24, 15 and 36. Now, first let us find the number which is divisible by these three numbers. Let us find the least number, that is the number which is divisible by 24, 15 and 36 is nothing but the least common multiple. So, we are going to find the least common multiple using the prime factorization method, that is using our, yes, fundamental theorem. So, we are going to split 24 as 2 power 3 into 3 power 1, 15 as 3 power 1 into 5 power 1 and 36 can be split as 2 power 2 into 3 power 2. Of these, we are going to find LCM. LCM is nothing but having the largest power of the prime numbers. So, 2 power 3 into 3 power 2 and into 5 power 1. So, multiplying we get 360 is the LCM of these numbers. That means, 360 is divisible by 24, 15 and 36, that is our least number, but we need the largest 6 digit number. So, let us take the largest 6 digit number which is 999999 and divide this number by 360. As we divide, we get the remainder as 279. Okay. So, this remainder says that this number is 279 more than the number which is divisible. So, to get the number which is divisible by 360, we should take off, we should remove or we should subtract that remainder. Yes, subtracting the remainder, we get the number which is divisible by these 3 given numbers. So, the answer is 999,720. So, this is the largest possible 6-digit number which is required. Okay, look at the sum. We are going to find the smallest number when divided by 3 numbers, that is 35, 56 and 91, which leaves remainder 7 in each case. So, we have to find the number which is divisible by the 3 numbers given. First, for finding that we need the LCM, that is the number, the least number which is divisible by these 3 numbers is the LCM of those 3 numbers. So, first let us find the LCM. For that, first we factorize these numbers. So, 35, 56 and 91 can be factorized in these ways. Using this, we are going to find the LCM. So, LCM is 5 into 7 into 2 power 3 into 13. Multiplying, we get 5 into 8 as 40, 7 into 13 as 91. So, multiply these two, get the answer as 3640 is the LCM of these numbers, but we need to find the number which should leave the remainder 7. So, that should be more than the LCM. How much more? The remainder, yes, 7 more, which means we are going to add 7 with the LCM. So, that is the required number. The required number is 3640 plus 7 or 3647 is the answer. Children, you have one more sum, that is our 6th sum as a homework. So, I want you to do that 6th sum using this theorem. Okay. Now, let us move on to the next sum, which is the last sum of this exercise. Now, we are required to find the least number which is divisible by the first 10 natural numbers. What are the first 10 natural numbers? Yes, 1 to 10. So, I have written all those numbers. We are going to find the LCM of these numbers. So, as LCM takes the highest power, we may leave the least powers. That is, we may leave as 1 is not a prime number. So, we can leave 1 and 2 power 1. Here it is 2 power 1. As 2 power 2 is there and 2 power 3 is there, we may leave these 2 numbers, that is 2 and 4 can be left out. And then 3 power 1, but here 3 power 2 exists. So, we can leave this 3 power 1 and take the LCM of the numbers which are remaining, that is no need to include 4, 3 and 2. So, we can have 5, 6, 7, 8, 9 and 10. So, let us split these numbers as factors and get the highest powers of the factors and multiply, get the LCM. So, the highest power of all those factors are written as product. So, 2 power 3 into 3 power 2 into 5 power 1 into 7 power 1. So, when we multiply, this is 8, 9, 5 and 7. So, 8 5s are 40. So, this is easier and 9 7s are 63. While multiplying, we get the answer as 2520. So, I think you have understood this theorem, that is the fundamental theorem, which is otherwise called as unique factorization theorem. Let us see in the next session afterwards. Goodbye, children.